All right, so we are going to look at chapter 13, section 6, which is solving equilibrium problems. And we're going to look at two problems. So the first one we're going to look at is number 59. And so here's kind of the key characteristic of number 59. So 59 has a k value where we are going to need to use the quadratic equation. So the first thing I'm going to do is I'm going to rewrite the equation from number 59. And we're going to make a table similar to what you would have looked at in your modeling all that equals. And the letters we're going to use here are ICE. So here the I stands for initial. The C stands for change. And the E stands for equilibrium. So I want to know the pressure of NO in equilibrium with N2 and O2 in a flask at initial pressure of 0.80 and 0.20 atmospheres respectively. So this is 0.80 atmospheres and this is 0.2 atmospheres. And so since it didn't give us an initial value of NO, we're going to assume it's 0. So in equations, the change, you're going to use up reactants. So we're going to subtract from our reactants and we're going to make products. So we're going to add to the product side. And we're going to use X. So here, the coefficient for N2 is a 1. So this is X. The coefficient for O2 is a 1. We're going to make this X. And the coefficient for NO has a 2. So we're going to make this 2X. So my equilibrium looks like this: 0.80 minus X, 0.20 minus X, and then 2X. Okay, so then we're going to set up our K expression. Now we're actually given the value of K here. So K would be equal to 0.050. And we know that this is products, so this would be NO. And these are actually pressures, so I'm going to make these parentheses. And this would be squared. And then the concentration of N2 to the first power and O2 to the first. Okay. So the equilibrium for NO is 2X, and we're going to square that. And then on the bottom, we're going to have 0.80 minus X and 0.20 minus X. All right, so we're going to do a little reducing here. So we're going to take my 2X and square it. So we're going to get 4X squared. And on the outside, on the bottom, we're going to dissolve. So we're going to use our FOIL method. And so we should get 0.16 minus 0.80X minus 0.20X plus X squared. And this is going to be equal to 0.050. Okay, and then we're going to take and we're going to leave our 4X squared on this side. And we're going to take our 0.050 and multiply it by my 0.16 minus 1.0x plus x squared. And so we're going to get 0.008 minus 0.50x plus 0.050 x squared. All right, now if we're going to use the quadratic, then we want to set all this equal to 0. So we're going to have to move that forward so everything's on one side. Okay. So I get 3.95 x squared plus 0.050 x minus 0.008. Now on my graphing calculator, I have the quadratic program. And so the way that works is it asks me for the value of A, then it asks me for the value of B, and then it asks me for the value of C. And when you solve, X has two values. So X can either be 0.039 atmospheres or negative 5.2 times 10 to the negative second atmospheres. And we can't have a negative number. So that marks out this. So now I know the value of X. All right. And so what I really want to know is the pressure of NO. So we're going to go back up to my ice table here. And so this is what I'm looking for. So the pressure of NO would be equal to 2 times my 0.039 atmospheres. And so we're going to get an answer of 7.8 times 10 to the negative second atmospheres, or 0.078. All right, so that's the first problem we're going to look at. And that's a problem where we're going to have to use a quadratic. And so the second one we're going to look at is number 64. Now, in number 64, we can use a method called approximation. And so here's kind of the key idea in order for us to be able to use an approximation. So if you take the K value and you multiply it by a factor of 100, and this is less than your initial concentration, this tells us that the change in your concentration, which is X, will be small, and that's, we can use approximation. Okay, so again, I'm going to set this one up like I did the last one. The first thing we're going to do is we're going to write the equation. And we're going to make ourselves an ice table. And it tells me that I have 2 moles of CO2 that's placed in a 5-liter vessel. And we need to know the equilibrium concentrations of all species. Okay, so since it only gave me initial value of carbon dioxide, we're going to assume that the initial values of the products are 0. And so they've given me what I need to calculate molarity. So you're going to actually need to take your 2 moles and divide it by the 5 liters and to give you your molarity, which is 0.40 molar. Okay. So again, we're going to use up reactant and we are going to make product. And so my coefficient for CO2 is a 2, so we're going to have 2x here. So this is 0.40 minus 2x. And then CO has a coefficient of 2x, so we have 2x here. And then oxygen's coefficient is a 1, so it would just be x. Okay, so when we're using approximation, What we're really going to do is we're going to ignore the amount of X we're subtracting from our reactant. All right, so K is going to be equal to my products, so CO squared times O2, over my reactant, which is CO2, and its coefficient is a 2. And it gave me the value of K in the problem as 2.0 times 10 to the negative 6. And so on the top here, we're going to have 2x squared times x. And on the bottom, we're going to have 0.40 molar. And that'll be squared because the coefficient is a 2. Okay, so I'm going to start by reducing what I have on the top here. So we're going to get 4x cubed. And then I'm going to square my 0.40 and multiply it by my K value. And we get 3.2 times 10 to the negative 7th. We're going to get x cubed by itself. And then we're going to take the cube root of both sides. And so when I do that, x is going to be equal to 4.3 times 10 to the negative 3rd. And this would be concentration, so it's going to be molar. All right, so then we're going to have to go back in and we're going to have to plug all of this into our ice table. Okay. So if I start with O2, remember that O2 is equal to X. So this would be 4.3 times 10 to the negative 3rd molar. If I go to CO, remember that this is 2X. So we're going to take 2 times 4.3 times 10 to the negative 3rd molar. And so we're going to get 8.6 times 10 to the negative 3rd. And then if I'm going for CO2, we're going to have 0.40 minus 2x. So we have 0.40 minus 8.6 times 10 to the negative 3rd molar. And so my answer here is going to be 0.39 molar. Okay, so those are the two types of problems that you're going to see when we're solving equilibrium problems where I do not give you the equilibrium concentrations. You're finding those values.